After designing the inner control loops, we must define the control tasks for each converter to ensure proper operation of the wind turbine. This section introduces the outer control loops of the wind turbine and explains how they provide reference signals to the inner loops. This table shows the nomenclature and controller parameters used in this section. There are two control approaches for variable speed wind turbines: power mode control and speed mode control. They are illustrated in figures 35 and 36 respectively. These approaches operate the turbine along a desired power-speed curve. Here we use the MPPT curve described in Section 2. The next section will explain other possible curves. In power mode control, we first measure the rotor speed of the turbine. Then we use the MPPT curve stored in a lookup table to determine the reference power to send to the converter. Since the MPPT curve relates rotor speed to mechanical power, we subtract the corresponding power losses to obtain the reference electrical power. See Figure 27 in Section 8 for a description of power losses. In power mode control at high wind speeds, the rotor speed is controlled by the pitch angle. Once the rotor speed reaches its rated value, the pitch angle controller increases the pitch angle to maintain the speed at its rated value.
In speed mode control, we use the converter power to determine the reference speed via the MPPT curve. Next, a proportional integral controller adjusts the converter reference power to control the speed at the reference value. As in the previous approach, power losses must be considered when calculating mechanical power from measured electrical power. In speed mode control at high wind speeds, the turbine power is controlled by the pitch angle. Once the turbine power reaches its rated value, the pitch angle controller increases the pitch angle to maintain the power at its rated value. According to Reference 5, power mode control most closely reproduces the control system of wind turbines in practice. Therefore, this study will use power mode control.
Additionally, there are two control approaches for the grid-side and machine-side converters. These approaches differ in the control tasks assigned to each converter. Here, they will be referred to as approaches A and B. In approach A, the grid-side converter controls the DC bus voltage in cascade from the active power delivered at the point of common coupling, and the machine-side converter controls the power extracted from the wind by adjusting the Q-axis component of the generator stator current. In approach B, however, the grid-side converter controls the power extracted from the wind by adjusting the delivered active power, and the machine-side converter controls the DC bus voltage in cascade from the Q-axis current. Approaches A and B manage active power differently but reactive power similarly. In both cases, the grid-side converter controls the reactive power at the desired set point, and the machine-side converter controls the D-axis current to 0.
Figure 37 shows a schematic of a wind turbine using approach A. In this approach, the grid-side converter controls the DC bus voltage, and the machine-side converter controls the power extracted from the wind. Figure 38 shows a schematic of a wind turbine using approach B. In this approach, the grid-side converter controls the power extracted from the wind, and the machine-side converter controls the DC bus voltage. Figures 37 and 38 illustrate the control implementation with current and voltage measurements taken in the stationary ABC reference frame. However, as explained in Section 5, we use the synchronous DQ reference frame to represent three-phase signals in simulations and small signal analysis. In this study, we will use approach B because it provides the grid-side converter more control flexibility for grid code compliance and grid support services. Meanwhile, the machine-side converter is in charge of DC bus voltage control. In summary, we will use power mode control and approach B to control the wind turbine.
Now we will describe the design of the DC bus voltage control. This design is based on the DC voltage dynamics described in Section 7. First, we will rewrite the DC voltage dynamics in a form suitable for control design. By multiplying both sides of equation 95 by VDC and using the relationship between converter voltages and modulation indices defined in equations 98 through 101, we obtain equation 189.
Then, defining the DC side powers of the machine side and grid side converters results in the DC voltage dynamics 190. As previously mentioned, approach B controls the DC voltage using the Q-axis current of the machine side converter, ISQ. Therefore, we will rewrite the DC voltage dynamics as a function of this current. To accomplish this, we use power and electrical torque definitions. Next, we simplify the power, PS, by neglecting the stator resistance and considering the zero D-axis current condition. Substituting equation 194 into 190 yields the DC voltage dynamics as a function of the desired Q-axis current component.
Second, we perform a procedure similar to that used to design the current control loops. Defining the auxiliary control UDC in equation 196 yields a linear system in the general form used for designing proportional integral controllers in section 9. Equations 198 and 199 represent the proportional integral controller. See the table at the beginning of this section for controller specifications and gains. After calculating the UDC signal from equation 198, the reference current is obtained from the definition of the auxiliary control. Finally, the Q-axis reference current, which is sent to the inner current control loop, is obtained by passing the reference signal in equation 200 through a low-pass filter. This filter limits the reference bandwidth. Figure 39 illustrates the inner loops used for current control and the described DC voltage control. In the next video, we will discuss frequency control challenges in power systems with high renewable energy penetration. We will also describe deloading methods to enable wind turbines to participate in system frequency control. Thank you very much, and follow us for more content like this.